Good morning, everyone. I'm Rahul Chowdhury, and welcome to our comprehensive course on threading in operating systems. Today we're going to dive deep into one of the most fascinating and essential concepts in modern computing: how programs can execute multiple tasks simultaneously through threading. We're starting with an introduction to threading in operating systems. This foundational topic will set the stage for everything we'll learn throughout this course. First, we'll explore the fundamental difference between threads and processes. Understanding this distinction is crucial because many students initially confuse these two concepts, but they serve very different purposes in system design. Threads are lightweight execution units. Think of them as mini processes that can run independently within a single program. Unlike processes, threads share memory space, which makes them incredibly efficient for certain types of applications. This brings us to concurrent programming, the art of designing programs that can handle multiple tasks at the same time. In today's world of multi-core processors and complex applications, this isn't just a nice-to-have feature. It's absolutely essential for modern applications. Whether you're building a web server handling thousands of requests, a video game rendering graphics while processing user input, or a mobile app downloading data while maintaining a responsive interface, threading makes it all possible. We'll also examine different application models, comparing single-threaded versus multi-threaded approaches. Each has its place, and understanding when to use which approach is a key skill for any systems programmer. By the end of today's session, you'll have a solid foundation in threading concepts that will prepare you for the more advanced topics we'll cover in subsequent lessons. Let's begin this exciting journey into concurrent programming. Now let's dive into one of the most fundamental distinctions in concurrent programming. Building on our introduction to threading concepts, we need to clearly understand the differences between threads and processes. This comparison will help you understand when to use threads versus processes in your programs, and why threads have become so important in modern computing. Let's start with processes. A process is like having your own private apartment. You have complete independence and your own dedicated memory space. As you can see, processes have independent memory spaces, which means they're completely isolated from each other. Creating a process is heavyweight because the operating system needs to allocate separate memory, set up new page tables, and initialize various data structures. Threads, on the other hand, are like roommates sharing the same apartment. They live together and share common resources. Threads within the same process share memory space, making them lightweight to create. They can directly access the same code, data, and files, which enables efficient communication but also introduces the need for careful synchronization, something we'll explore in detail in upcoming lessons. This fundamental difference in resource sharing is why threads are preferred for tasks that need to work closely together, while processes are better for completely independent tasks that need strong isolation. Now that we've established the differences between threads and processes, let's dive into understanding how threads actually behave during their lifetime. We're going to explore the thread lifecycle, the different states a thread can exist in from creation to completion. This diagram shows us the 5 fundamental states that every thread goes through during its life cycle. Think of this as a roadmap that describes exactly where a thread is and what it's doing at any given moment. First, we have the new state. When you create a thread in your program, it starts here. It exists in memory but hasn't actually begun executing yet. The thread object is created, but the operating system hasn't allocated CPU time to it. Next is the ready state. Here, the thread is prepared to run and is waiting in the scheduler's queue for its turn to use the CPU. This is like standing in line. The thread has everything it needs to execute. It just needs to wait for the processor to become available. The running state is where the action happens. The thread is currently executing its instructions on the CPU. Only one thread per CPU core can be in this state at any given time, which is why thread scheduling is so important. When a thread enters the blocked state, it's temporarily suspended because it's waiting for something. Maybe a file to be read, user input, or access to a shared resource that's currently locked by another thread. The thread can't continue until that condition is met. Finally, the terminated state marks the end of the thread's life cycle. The thread has completed its work, either successfully finishing its task or being terminated due to an error or external request. Notice how threads can move between these states multiple times. A thread might go from running to blocked when it needs to wait for data, then back to ready when that data becomes available, and then to running again when the scheduler gives it CPU time. Understanding these transitions is crucial for writing efficient multi-threaded applications. Now that we've explored thread scheduling algorithms, let's dive into the different types of threading models and how they're implemented in modern operating systems. There are three main types of threading models, each with distinct characteristics and use cases. Let's examine each one carefully. First, we have user-level threads. These are managed entirely by the application itself, making them completely invisible to the operating system kernel. This approach offers fast context switching since no kernel intervention is required, but it also means that if one thread blocks, the entire process blocks. Kernel-level threads, on the other hand, are managed directly by the OS kernel. This provides better multiprocessing support since the kernel can schedule threads across multiple CPU cores, but it comes with higher overhead due to system calls for thread operations. The hybrid model combines both approaches, using user-level threads that are multiplexed onto kernel threads. This gives us the benefits of both models while mitigating some of their individual drawbacks. Now let's look at the thread mapping models, which define how user threads are mapped to kernel threads. Many-to-one mapping means multiple user threads are mapped to a single kernel thread. This is efficient but limits true parallelism. One-to-one mapping provides each user thread with its own kernel thread, offering true parallelism but with higher overhead. Finally, many-to-many mapping multiplexes many user threads onto a smaller number of kernel threads, providing a balance between performance and resource usage. This is the most flexible approach and is used by many modern threading libraries. Now that we've covered the fundamental threading concepts and models, let's dive into one of the most critical aspects of concurrent programming, the challenges that arise when threads share resources. Today, we're exploring thread synchronization challenges, the problems that can make or break a multi-threaded application. First, let's examine race conditions. These occur when multiple threads access shared data concurrently, and the final result depends on the unpredictable timing of thread execution. Imagine two threads trying to increment the same counter. Without proper coordination, updates can be lost. This brings us to critical sections, segments of code that must execute atomically without interruption. These are the danger zones where race conditions typically occur, and they require special protection mechanisms. When critical sections aren't properly protected, we get data inconsistency corruption in shared memory access that can lead to incorrect calculations, corrupted files, or system crashes. This is particularly dangerous in financial or safety-critical systems. All of these problems highlight the fundamental need for synchronization mechanisms. We need tools and techniques to coordinate thread execution, ensuring data integrity while maintaining the performance benefits of multi-threading. These synchronization challenges are at the heart of concurrent programming. Understanding them is crucial before we move on to explore the specific mechanisms and tools designed to solve these problems in our next section. Now that we've identified the challenges in thread synchronization, let's explore the specific tools and mechanisms that help us solve these problems. These are called synchronization primitives, fundamental tools that operating systems provide to coordinate thread execution and ensure safe access to shared resources. First, we have mutexes, short for mutual exclusion locks. These are binary locks that protect critical sections by allowing only one thread at a time to access shared data. Think of it as a bathroom key. Only one person can hold it at a time. Semaphores are more flexible counting mechanisms. Unlike mutexes, they can allow a specific number of threads to access a resource simultaneously. They're perfect for resource management, like managing a parking lot with limited spaces. Condition variables provide thread coordination through weighting and signaling. They allow threads to efficiently wait for specific conditions to become true, rather than constantly checking, like waiting for a notification instead of repeatedly asking, "Are we there yet?" Finally, atomic operations are indivisible read-modify-write operations that complete without interruption. They're the foundation of lock-free programming and ensure that simple operations like incrementing a counter happen safely without explicit locks. These four primitives form the toolkit that developers use to build robust, multi-threaded applications. Each has its specific use cases and performance characteristics that we'll see applied in real systems. Now we're going to tackle one of the most challenging problems in multi-threaded programming: deadlock. Building on the synchronization primitives we just covered, let's understand how threads can get stuck waiting for each other indefinitely. A deadlock occurs when we have a circular wait for resources among threads. Picture this. Thread A holds resource 1 and waits for resource 2, while thread B holds resource 2 and waits for resource 1. Neither can proceed, creating a permanent standstill. For a deadlock to occur, 4 specific conditions must all be present simultaneously. These are known as the Kaufman conditions, and understanding them is crucial for both preventing and detecting deadlocks. The 4 necessary conditions are: mutual exclusion resources can't be shared, hold and wait threads hold resources while requesting others, no preemption resources can't be forcibly taken away, and circular wait, a cycle of threads each waiting for the next thread's resource. The good news is that we have strategies to deal with deadlocks. We can either prevent them from happening in the first place or detect and recover from them when they occur. Prevention techniques include resource ordering, always acquire locks in the same order, and timeout mechanisms, don't wait indefinitely for a resource. Detection algorithms can identify deadlock cycles and trigger recovery procedures like process termination or resource preemption. Understanding deadlocks is essential because they can bring entire systems to a halt. Next, we'll explore how these concepts affect threading performance and what trade-offs we need to consider. Now that we understand how deadlocks can paralyze systems, let's examine threading performance considerations. When we move from theory to practice, performance becomes crucial. Even the most elegant threading solution is worthless if it's too slow. First, let's talk about context switching overhead. Every time the CPU switches between threads, it must save the current thread's state and restore the new thread's state. This includes registers, program counter, and stack pointers. This overhead can quickly add up in systems with frequent thread switches. To mitigate this overhead, we use the thread pool pattern. Instead of creating and destroying threads constantly, we maintain a pool of reusable threads. This dramatically reduces the cost of thread creation and provides better resource management. The threads wait for work in a queue, eliminating the expensive create-destroy cycle. Load balancing is equally important. We need strategies to distribute work evenly across threads. Static assignment can lead to some threads being overloaded while others remain idle. Dynamic work distribution and work stealing algorithms help maintain optimal thread utilization. Finally, memory locality plays a crucial role in multi-threaded performance. When threads access data that's already in the CPU cache, performance improves dramatically. However, when multiple threads compete for the same cache lines, we get false sharing, which can devastate performance. Data structure design becomes critical in multi-threaded environments. These optimization strategies work together to create high-performance multi-threaded applications. The key is understanding that threading isn't just about correctness. It's about balancing correctness with performance. As we'll see in our next assessment, measuring and optimizing threading performance requires careful consideration of all these factors. Excellent. Now that we understand the theoretical foundations of deadlock prevention, let's explore how threading is actually applied in real-world software systems. This final section will show you where all these concepts come together in practice. First, let's look at web servers, one of the most common applications of threading. Modern web servers like Apache and Nginx handle thousands of concurrent client requests by creating separate threads for each connection. This allows them to serve multiple users simultaneously without blocking. Database systems are another excellent example. Systems like PostgreSQL and MySQL use threading for parallel query processing and transaction management. Multiple threads can work on different parts of a complex query simultaneously, dramatically improving performance. Gaming engines showcase sophisticated threading architectures. They typically separate graphics rendering, physics calculations, and user input processing into different threads. This ensures smooth gameplay, even when one subsystem is under heavy load. Media processing applications like video encoders use threading extensively. They can encode, decode, and stream content in parallel, making real-time video processing possible. Think about how streaming services handle millions of concurrent viewers. Finally, we have best practices for production systems. These include proper thread pool management, careful synchronization design, and thorough testing for race conditions and deadlocks, all the concepts we've covered in this course. And with that, we've completed our comprehensive journey through threading in operating systems. We started with basic concepts, explored thread lifecycle and scheduling, examined synchronization challenges, and now see how it all applies in real-world systems. Remember, threading is a powerful tool, but with great power comes great responsibility. Always design with synchronization and performance in mind. Thank you for your attention, and I hope you'll apply these concepts effectively in your future projects.